So chapter 2, we're going to talk about measurements. We're going to talk about how to take measurements. We're talking about significant figures. We're also going to talk about conversions. We're going to talk about dimensional analysis, as we talked about the other day. Again, they do a certain understanding of things to go through 1A and 1B, and one how to do dimensional analysis sort of correctly, showing the units and everything. The chapter here talking about density, if I'm not mistaken. So let's get into sort of measurements here. So measurements are really important, and a measurement is really important to always make sure that you include units. You know, units are extremely important. Reason for that, again, is if I wrote, 100 down, really, who knows what I'm talking about? 100 is just a number. It has no really frame of reference or anything like that. It could be 100 pennies, right? Which would be very different than if you had $100, which would be very different than it's like 100 degrees outside, which again, it always seems lately it is 100 degrees outside a lot. So whenever you take any type of measurement, you should always include not only the number, but also the unit as well. So we do want to always have the number and the unit associated with it. When we talk about units, there really is a couple of different types of units that we come across. Pretty much, we use the English system, and pretty much everybody else uses the metric system. And that obviously could create a lot of problems, especially when the world got smaller in terms of everybody sort of doing business with each other. So in 1960, they actually got together, and in chemistry and in science in general, they came up with what is sometimes referred to as the SI unit of systems the SI units. The SI units is really based off of the metric system. And you'll hear a lot sometimes in chemistry, the SI unit of this is that, the XI unit of this is that. Okay. And let us initial next to your name, not just an X. Yes, like your initials, like you're signing something. All right. All right. I know one person did and we all followed. It's all right. Let's not go over the cliff together later. All right. So the SI unit, you'll sometimes hear a lot. It really is based off of the metric system and so forth. We'll talk about each of these here in just a second. So first off, though, let's take a look at the SI units and really the quantities that go with them. Mass is the kilogram. So the basic SI unit for mass is kilogram. Although really, for the most part, when we do measure the mass of something, we do a lot of times measure in the units of grams. Is usually a more convenient unit that we use. Length, the unit there is meters. And we do see, as we'll see later, centimeters, millimeters. These are units that we come across a lot. The SI unit for time is seconds. And the SI unit for temperature is one you might not be familiar with, but if you take a lot of chemistry courses, you will be very, very familiar with, and that is Kelvin. And Kelvin is a unit that pretty much, I would say about 98, 99% of the time, if you're doing some type of chemistry formula that involves temperature, it is the Kelvin that it needs to be in. So we'll use that a lot. One thing that we'll talk about is in terms of Kelvin, it's not degrees Kelvin or anything like that. It is just Kelvin. So we don't use the little degree symbol. We don't say degrees Kelvin. So you had like 454 Kelvin is how you would say it, and also how you would write it. So let's take a look at some common sort of length measurements. And remember that some of these, they do want you obviously to sort of know, and a lot of them we do kind of use a good amount of times. 1 meter is 39.37 inches. I would say 1 centimeter is 0.01 meters. So that is a relationship, meters and centimeters, that's used a lot. That is also equivalent to that there are 100 centimeters in 1 meter. And we get that by dividing by 0.01 and so forth. We got everybody this time, yeah? All right. So again, we get that 100 to 1 by dividing the 0.01 to the other side. 1 kilometer is 1,000 meters. That is something that, you know, you should know, and we do come across a lot. I would say very common sort of units of length, centimeters, meters, kilometers are ones that we do come across a lot in chemistry, and you should know, again, the sort of conversions between those guys. One way that we sort of manipulate metrics, measurements, is to use prefixes. And this is a table of certain prefixes. And I would say through your chemistry career, you're probably hit most of these on here. We do in this class come across a lot of kilo, centi, milli. You go to 1A and stuff like that, you'll probably hit some micro, and nano will come up a lot, and maybe mega as well. So these are the meanings, and what this is how much of the base unit in the prefix unit, in one prefix unit. The base unit, for example, here would be meters, I think, or there was meters, for example, and kilometers would be the prefix unit. Meters would be the base unit. So as we saw before, 1 centimeter is our 0.01 meters, or again, dividing it out gives us our 100 centimeters is 1 meter. We also see that in kilo, there is 1,000 meters in 1 kilometer. So again, those are some relationships that we could get from here. Although they don't want you guys, for some reason, to use these, I think it's good to know. So these are the power of 10 sort of, the power of 10 conversions for each of these prefixes. And I would say most of the time, if you find a table or something like that, that is what you're going to see. I would also say that most of the time people do the conversion backwards and they always mix it up. So this also is how much of the base unit there is in one of the prefix units. So for example, if we took centi, that would mean in 1 centimeter, there is 10 to the minus 2 meters, and that is where it should go. So the 10 to the minus 2, 10 to 3, 10 to 4, whatever it may be, that is what goes on the base unit for one of the prefix units. And it's really common, people like to kind of flip those guys around and kind of use them backwards. If we looked at our kilo, 1 kilometer would be 10 to the 3 meters. 10 to the 3 is 1 times 10 to the 3 in scientific notation. That is basically what that means. And it's basically 1,000, like we saw above. So again, it's very common, people will reverse those things. Now, it doesn't matter the base unit. The prefix works the same for everybody. So if I didn't have meters, but I had 1 kilogram, that would be 10 to the 3 grams. So it works the same here. The base unit is grams on both of them, but the prefix works the same. Also, you know, if I had 1 kiloliter, that would be 10 to the 3 liters. So again, it doesn't matter what base unit is, the prefix basically works that way. So every number that you see either here or here, which by the way, they are the same numbers, one's just in decimal form and one is in scientific notation, is how much there is in the base unit to one of whatever the prefix unit is. Any questions on that there? Definitely should know kilo, centi, milli, probably nano as well. They'll probably come up. So make sure you kind of know those guys. The relationship between inches and centimeters, inches being the English units, centimeters obviously being the metric units here. And this is definitely the conversion they definitely want you to know. It's like the popular one. 1 inch is 2.54 centimeters exactly. So there's an exact conversion between them. But that's a ruler, in case you're not sure, but that is a ruler there. And we should know how to look at a ruler, by the way. Big numbers up on top are inches, yes. Big numbers on the bottom are centimeters. Little dashes on the bottom are millimeters, yeah. So there's 10 millimeters in a centimeter. So if you count the little dashes, there's 10 dashes between. So the little guys are millimeters, yeah. So just kind of circle the little guys, millimeters. Let's talk a little bit about volume. Volume is the amount of three-dimensional space that is occupied by a substance. The SI unit for volume is meters cubed. Nobody really uses that one, but there are really a couple of conversions here that we use a lot, and it's really these two right about there. 1 cubic centimeter is equal to 1 milliliter, and 1 liter is 1,000 milliliters. So these are definitely ones that we come across a lot here, and you definitely should know. Those are all units of volume, and you might be wondering about the cubic centimeters or even the cubic meters. One way that you could calculate a volume like you'll do in lab today is to take the length times the width times the height. And each of those length measurements, if they were done in centimeters, that would be centimeters times centimeters times centimeters, which gives you your cubic centimeters. So that is a volume. Each of these individual ones are length measurements. So each of those individual ones are length measurements. When you multiply them together, calculation number 1 is what you'll do there. In the lab, you'll get cubic centimeters in that particular case. Any questions on that there? Now, again, a cubic centimeter is equal to 1 milliliter, and you will sometimes see it written 1 cc. Yeah, like if you watch medical shows, give that guy 5 cc's before he dies. 5 milliliters is basically what they're given. So in chemistry, cubic centimeters in this version is typically what we use. Milliliters and cubic cc is sometimes used in sort of medical applications for it. Cubic centimeters are usually used to a lot of times get the volume of a solid, while milliliters obviously is a volume of a liquid. Please stop taking pictures every 2 seconds. I appreciate it. Take some notes with a pen. The units of mass is another common units that we do. So mass is basically the amount of matter there is an object. Matter is anything that occupies space and has mass. The SI unit for mass, like I said, is kilograms, but really grams is a very common unit. So definitely the relationship between grams and kilograms is something we use a lot. There are 1,000 grams in 1 kilogram. So that is definitely a relationship we use a lot here. Grams, kilograms, and milligrams are also another very common unit. So milligrams we do see a lot. Milli is the same conversion we saw there for liters. 1 gram, is equal to 1,000 milligrams. Yeah. So just like 1 liter is 1,000 milliliters, 1 gram is equal to 1,000 milligrams. We obviously will measure mass using a tool such as this, which is referred to as a balance. That's an electronic balance or an analytical balance. You have them in the lab and you'll use them today as well in lab. It's a fancy word for scale, basically, right? It measures the mass of an object. Now, there is actually a difference between basically the word weight and mass. The weight of an object is affected by the force of gravity that's exerted on it, and the mass of an object is sort of independent of the force of gravity. So if you weigh yourself here versus the moon, you'll be about like 1/6 the weight there on the moon. So that's good. But the mass will be the same. So in chemistry and most sciences, when we sort of do the process known as weighing, which is why a lot of people call it the weight, we actually will refer to it as the mass of the object. So you should refer to it as the mass of the object in chemistry when you do go weigh out something, and not really the weight of the object. We talked a little bit about the temperature, that the SI unit is Kelvin, but there really is 3 different temperature scales that we do come across. One is degrees Fahrenheit, one is degrees Celsius, and one, as I mentioned earlier, is Kelvin. Again, the main difference, or one of the main differences, is we again do not use the degree symbol there with Kelvin, but we do use it with Fahrenheit and Celsius. Fahrenheit scale, which is like with our temperature and stuff like that, water boils at 212 degrees Fahrenheit and freezes at 32 degrees Fahrenheit. Celsius, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. And at 375 Kelvin, it will boil, and at 273 Kelvin, it will freeze water. The difference is really between sort of the freezing point and boiling point on each of these scales is really the basis of the conversion to go from one sort of temperature unit to the next. So let's take a look at each of these here. Looking at these scales, what we see is between freezing and boiling on both the Celsius and Kelvin scale, it's about 100 units difference between the two. When we go on the Fahrenheit scale, the difference between freezing and boiling is about 180 units. And that really affects how we convert between the two, or the 3 of them. So let's take a look at the formulas to do those conversions. And to convert between Celsius and Kelvin, which for the most part is pretty much what you do in chemistry, this conversion is the one you do the most, and that is the way you do it the most, which is take it from Celsius to Kelvin. You take the temperature in Celsius, you add 273 to it, and that will give you the temperature in Kelvin. The correct true number is 273.15. I would say most people don't use the 0.15 because it gets rounded off most of the time. I don't use the 0.15. I use the 273. So I'm good with the 273, but you might find somebody that still uses the 0.15 in case there. But it is temperature in Celsius plus that 273 gives you your Kelvin. Obviously, if you had to go backwards the other way, we would be subtracting. So the temperature in Celsius would be our temperature in Kelvin minus 273 to sort of go back the other way to convert it. Converting between Fahrenheit and Celsius, we take the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. And if we wanted Celsius from Fahrenheit, we would take the Fahrenheit minus 32 divided by 1.8. And the 1.8 there is the same as 9/5. If you learned that maybe a fraction years ago, it's the same deal. Now, there is sort of a special rule that people follow when we're dealing with strictly just temperature conversions. And if all you're doing is taking a number from one temperature scale to the next, there's sort of a rule that we follow for what the answer should look like. And it really doesn't follow strict significant figure rules. It just follows this general rule. And the general rule is whatever the original number looked like, the converted temperature number should look the same. So if the original number was a whole number, when you do the conversion, you should convert it to a whole number. If the original temperature number went to the first decimal point, you should convert it to the first decimal point. So that is the general rule that you follow when you're doing just strictly temperature conversions. The reason for that is there's a lot of variations in these formulas. As you can see here, 1.80, some people just use 1.8, some people use the fraction. So it doesn't really follow significant figure rules super strictly. And that is the general rule that most everybody sort of follows. Any questions on that? All right, why don't we try some here? Take a moment or two and do these conversions. Okay, let's take a look. So the first one here is we're going from Celsius to Kelvin. So that is going to be the temperature in Kelvin would be our temperature in Celsius plus a 273. So we'll do a 28.5 plus a 273. Gives us 301.5 Kelvin. Once again, original number 1 decimal place. We want to take it to 1 decimal place and no degrees on that. So just Kelvin. Any questions on that one? Here on the second one, we're going from Celsius to Fahrenheit. So that is going to be our temperature in Fahrenheit is equal to 1.8 temperature in Celsius plus a 32. So that'll give us 1.841 plus a 32. That's going to give us 1.8 times 41 plus a 32. That's going to give us 105.8 degrees Fahrenheit. Now on this particular one, if we look at our original number, it is a whole number. So we would want to actually round this one to a whole number. And we would want to end up at 106 degrees Fahrenheit. Again, following that sort of rule of making our converted number look like the original number. Any questions on that one there? Lastly, here we're going to go from Fahrenheit to Celsius. So our temperature in Celsius is our temperature in Fahrenheit minus 32 divided by 1.8 gives us $1.60 minus 32 divided by 1.8 gives us 71.111. Lots of ones. And looking at our original number here, it is a whole number. So we would probably take this guy here to 71 degrees Celsius. Any questions on any of those temperature conversions? So you do need to know how to do these conversions. Again, the formulas will not be provided for you, so you need to know how to do them. I would say probably outside of chapter 2, you're pretty much stuck on Celsius to Kelvin. Maybe Kelvin back to Celsius is probably the main one. Probably won't see much of Fahrenheit anywhere, usually in a chemistry textbook outside of chapter 2. But you still need to know how to do the other ones. But definitely the Kelvin Celsius one is the one you'll have the most. Any questions on that? All right, so as we talked about as well, it's really important to make sure that you understand when you look at a unit, what it is referring to. Is it referring to a mass? Is it referring to a volume? Is it referring to a length? So you don't come up to somebody and say, I measured 50 milliliters for my mass, because that's a volume, right? Or, you know, I didn't have a volume that was 400 grams or something like that. So obviously here we have Kelvin, and as we've been talking about, that is a unit that represents temperature. Here we have liters, which is a unit that represents volume. This is meters, which is a unit that represents length. And lastly here, these are kilograms, which is a unit that represents mass. So it's really important to have that connection of what the unit actually does represent. Also a good time to talk about a couple of different types of sort of observations that we make. One is qualitative. Qualitative basically consists of general observations about the system. it was turned purple. We had a solid form. There was bubbles, those type of things that occur. Really, qualitative has nothing to do with any type of measurement. That is pretty much quantitative. So anytime you take a measurement that is a value and a unit associated with it, that is a quantitative observation, which is really a measurement in this case. If you continue on to 1B, they do a bunch of qualitative analysis experiments where frankly there's like nothing to calculate other than you observe what happens. Like you put these together, you get a solid, you put these together, it just dissolves. So that's again qualitative. Pretty much everything we do in this class in terms of experiments and stuff like that will be quantitative, where you will take measurements. There is some qualitative aspects, obviously, where, when you do observe something like, hey, I made a solid, it was a white solid, it was a yellow solid, whatever it may be, there's some qualitative analysis that you do in the class. When we write numbers in science, a lot of times we do come across a lot of numbers that are really large and a lot of numbers that are really, really small. And usually really large numbers or small numbers, big exaggerations of examples of that there, do have a lot of zeros. And if we do keep all those zeros along with our calculations, there's a pretty good chance you're going to screw up and lose a zero somewhere along the way in your calculation. So to handle really large numbers and really small numbers in chemistry, we use what is known as scientific notation. And scientific notation has a general format that we do follow, and it is this one right here. It is n times 10 to the n. First off, this first is a number between 1 and 10. That means it needs to be a number between 1 and 10. It can't be 10, can't be 20, can't be like point something, can't be 100. It needs to be a number between 1 and 10. Times 10 to the little guy there. And this guy can be obviously a whole number, but it could be positive or negative, depending really on which way you move the decimal place to get yourself to a number that's between 1 and 10. So if we had 453, we would go one place, two places to the left. That would give us 4.53 times 10 to the 2. We went two places to the left, so the exponent is positive. We had 0.001334. We would go 1, 2, 3 places. 1.334 times 10 to the minus 3. And again, it would be a negative exponent in this particular case. For the most part, if it's a large number, it's a positive exponent. If it's a small number, it's a negative exponent. Obviously, if you're going the opposite way, if you have the negative exponent, get into a decimal, you move the decimal to the left. Positive exponent to go to a decimal, you go to the right. So let's take a look at some of these examples here and see how we get there. We have 568.762. To get us there, we do need to go 1 and 2 places to the left. Gets us 5.68762 times 10 to the 2. To get us to a number between 1 and 10, we got to go 1, 2, 3, 4, 5, and 6 places to the right. And that gives us 7.72 times 10 to the minus 6. And obviously here, starting here, 1, 2, 3, 4 places there to the left to get us to 1.25 times 10 to the 4. And lastly, just one place to the right there gets us 1.35 times 10 to the minus 1. There's a reason why we keep some of the numbers and why we get rid of some of the numbers here, but a preview is you should never lose significant figures as you go from kind of decimal point form to scientific notation. So in terms of significant figures, and we'll talk about how to identify them a bit here, all these are significant. And when you write a number in scientific notation, all the numbers before the times 10 part are significant. So this guy's got 6 significant figures. All these numbers come before the times 10 part, and it is 6 significant figures. So anytime you write a number in scientific notation, all these numbers are always significant. By the way, none of these numbers were negative. That's just PowerPoint putting the negative sign in there. In this case, and we'll talk about these type of zeros as well, these zeros are not significant here, which means actually it only has 3 significant figures, which is why we dropped it off here when we went to scientific notation. Any questions on that there? All right. So obviously here, if we were going to do this 1, 2, 3, 4, and 5 places, gives us 4.25 times 10 to the 5th. We'll talk about it, but once again, these zeros are actually not significant, which is why we don't carry it over. So it actually has 3 significant figures. We have 1, 2, 3, 4, 5, 6, 7, I think. 8 times 10 to the minus 7 in terms of scientific notation. Any questions on how to write scientific notation? Scientific notation, do you have to use it all the time? The answer is no, I don't really care. But more importantly, your answers eventually should have the right number of significant figures when it's all said and done. And sometimes your only way to get it to the right number of significant figures is actually to write it in scientific notation, because you could control how many significant figures you need when you write in scientific notation. You know, for example, here, if I needed 2 significant figures, I could just write it like that, and now I have 2 significant figures. Now, more importantly, with scientific notation is where most people struggle, how to actually put it into your calculator correctly. So let's talk a little bit about how to put scientific notation into your calculator correctly so you hopefully get the right answer. All calculators that are scientific calculators should have an exponent button, and it will either say EE, may say EXP. And if you got kind of maybe a newer 2-tone type calculator, might have a times 10 to the n button. And usually those calculators also have like a little wheel on them. So if you have that type of calculator, we'll get to you in just a second, but we'll talk about the first ones here. When you go to put into your calculator a number in scientific notation, like 3.25 times 10 to the minus 8, you should not be using the multiplication button to do so. You should not be using the second or shift log button to do so. Shouldn't be using a caret to do so. You should actually be using the exponent button. So when you would go to put this in, you would go 3.25. You then would hit your exponent button, which would probably put something like 3.25 and an E, or it might do 3.25, pop up a couple of zeros up on top, maybe times 10 and a couple of zeros up on top. When you hit that exponent button, it represents this part of the number. It represents the times 10 part of the number, which means you don't need to hit the multiplication button. You don't need to do anything other than hit that button there. In addition to that button, your calculator does have a negative button or change the sign button, whatever you like to call it. And most calculators, it looks something like this, or it looks something like this. So at this point, you would then hit your negative button and then 8, and it would pop something in that looks like that. It would change this to an 8 and a negative, and that is the proper way to punch a number in scientific notation into your calculator. You want to always use your exponent button. No other buttons should you be using. Now, if you have this type of calculator, there's just a couple of extra things that you have to do because of the way typically these calculators are programmed. I'll just say maybe they're programmed wrong. They will do the math incorrectly if you don't put parentheses around every single number that's in scientific notation. So you have to put parentheses around every number in scientific notation. So if we were to do this, you would open a parentheses, do the 3.25, hit your exponent button, and it would go 3.25 times 10, and you'll have your little cursor blinking up there up on top. At that point, you then could hit your negative button and 8, and you'll end up with 3.25 times 10 to the minus 8 with your cursor still blinking up on top, which is not good sometimes depending on your calculator. That is where the wheel comes into play. You hit the little side of the wheel there, and it will bring your cursor back down where you can then close your parentheses and end up with it punched in like that. So you really do have to put parentheses around every single number. Works fine if you do that. If you don't do that, what it does is it, and a lot of calculators is it will kind of separate the calculation. It'll go like 3.25 and then times it by, you know, the second part of the number, stuff like that. Any questions on that? If you're not sure where your exponent button is, just come see me. We'll find it on your calculator and show you how to use it. But you want to always make sure you use it. One way you know that maybe you're not doing it right, especially when you're doing calculations, is you'll get an answer. Let's just say this was our answer. This part of the number will look good. This part will be off by a little bit. And that's usually an indication that you're not punching it in correctly. So why don't we try one just to make sure your calculators work. Let's do 4.1 times 10 to the minus 7 was divided by, just make it up, we'll go 3.25 times 10 to the 18. I'll do it as well. We'll see if we get the same answer. Just incorrectly, we would go 4.1. We would then hit our exponent button. We then would hit our negative button, hit 7, do our divide button. 3.25 exponent button. No need for the negative here since it's a positive exponent. Hit 18, then equals. And if we do all that good stuff there, we get something like 1.2615384 times 10 to the minus 25. We should really round it out to about there, 1.3. We'll talk about that later as well. But more importantly, you don't want to forget to record that part of it. It's very common. People just record the front part off their calculator and miss the times 10 part. You want to make sure you record it. Again, if you find yourself good on like the 1.26 part and the minus 25 parts off, it again is probably the way you're punching into your calculator, and that's what's causing the error. That is how you should display scientific notation when you give an answer. You should not write it like this, 1.3e minus 25. So don't do it with the e. You should write the times 10 part when you're writing it as an answer. Any questions on how to punch it into your calculator correctly? Probably more important than writing it on the paper is actually knowing how to punch it in correctly. By the way, obviously your calculator will not give you the right sig figs or necessarily the number in scientific notation every time, unless you programmed your calculator to give it to you in scientific notation. Just to keep that in mind. Any questions on any of that there? All right, so now we're going to talk about measurements and how to properly take measurements. And pretty much no matter what measurement is taken, there's always some degree of uncertainty that occurs with measurements. The degree of uncertainty basically is based on the equipment that you're using as to really how far you can sort of take a reading. So for example, if we had like a ruler, we'll do row ruler there. All right. All right, we'll go to sort of straightest ruler. There we go. All right, so say we had a ruler and we wanted to measure like this arrow on it. I'll spit that out. It's always important, no matter what piece of measuring device that you look at, that you figure out what does the scale really mean on it. So there's really two markings on most scales that you want to look at. One is sometimes referred to as the larger markings or the bigger markings. And in this case, the two big markings are really 1 and 2. So really our big markings, the difference is 1 centimeter difference between them. Now what you want to figure out is sort of the smaller markings and how many there are. When we count smaller markings, we typically start one past the last biggest marking, if you will. So this would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings basically between them. So there are 10 markings between basically 1 centimeter. That means that each of the smallest markings represent how much? How much of a centimeter does each of the smallest ones represent here? Basically 0.1 of a centimeter, right? So each one represents 0.1 centimeters. This would be like 1.1, right? 1.2, 1.3, 1.4, 1.5, 6, 7, 8, and 9. So there always is certain numbers that no matter who takes a peek at it, everybody should agree. And everybody really should agree here that this arrow is definitely 1.6 or so. So it definitely is 1.6. So we do want to record that. We would record 1.6. These are what are referred to as our certain numbers. Now we could clearly see that the arrow is not exactly on 1.6. It's not exactly on 1.7. And this is where the degree of estimation comes into play and the uncertainty comes into play. I may look at it and go, I think it's like halfway between the two, and maybe I record it as a 5 with centimeters written next to it, the units. Somebody else may look at it and go, I think it's closer to the 1.7. So maybe it's like, 1.66 or 1.67 or something like that as the reading. And that is the uncertain digit. And we should always record the first uncertain digit. Or sometimes referred to as estimated digit. And technically speaking, when you do that, that is how you should take a proper measurement. You should record all the certain numbers plus that first uncertain number. And believe it or not, when you do all those good things, that is what we like to refer to as significant figures. Which means this measurement here would have how many significant figures? It would have 3. All of it would be significant. It has the 2 certain values, the first uncertain value, and that would represent how many significant figures this measurement has. Now, in general, you could take the reading to one more place to the right of the smallest number. You can figure out sort of the precision of the equipment by taking the smallest marking and divide it by 2. So if I take 0.1 and divide it by 2, that gives me 0.05 centimeters. And sometimes people will record this as 1.65 centimeters plus or minus 0.05 centimeters. I personally am not big at recording the plus or minus part of it, but some people in the department are very big at recording the plus or minus part of it. Does it mean that last number needs to be 5? It doesn't. It just means you actually could take it to the second decimal place like we did obviously in our reading here. So that is sort of the degree of precision that you can get in this particular measurement. Any questions on that there? You do need to look at what you're using because scales can change. So let's say we had a wonderfully drawn graduated cylinder Probably why I failed art. It's all right. I'll get over it. All right. We'll call these milliliters. There's just bad quality control at the plant that day. That's why it's a little wobbly. So this is a graduated cylinder. It'll look just like the one you open up today and look at. Not really. When we do put a liquid in a glass container, we usually do see a sort of a phenomenon that occurs, which is the curvature of the liquid. I'll exaggerate it. That is what is known as the meniscus. And when we take the reading, we always read from the bottom of the meniscus. Sometimes it's easier to see than others. What's really happening, you'll talk about probably in Chem 1A, but what's really happening here is the liquid is actually more attracted to the container, to the walls of the container than itself. So it kind of runs up the sides. The true volume of where it's at is actually in the middle because it's not really running up the sides. So that's actually why we read to the bottom of the meniscus, because it's sort of artificially high on the sides because of that effect that occurs. So if we were to look at this, we would still want to look at our scale, and we see that the big markings go from 10 to 20 milliliters. That is a difference basically of 10 milliliters. Once again, if we start counting here, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between 10 and 20. That means each of the smallest markings in this particular case is how much? 1 milliliter in this case, yeah? So each of the smallest markings here is 1 milliliter. Obviously, this would be 11, 12, 13, 14, 15, 16, 17, 18, 19, and obviously 20 up there on top. Now, if we take a look at where our meniscus is, not very straightly drawn, but we'll go right about there. Everybody should see it is at least 15, so we would want to record 15 here. Once again, we do have some type of estimation, so maybe you don't feel it's exactly half. Maybe you feel it's more like to there, about 0.4. We would do our milliliters. Once again, this is the certain numbers, right? This is the first uncertain number. This number would have how many significant figures? Would have 3 significant figures. We could also figure out our precision by taking 1 divided by 2, 0.5 milliliters, right? Which basically shows us we could go to the first decimal place, which is where we took the reading to in this case. So some people may report this as 15.4 plus or minus 0.5 milliliters in terms of the precision. Again, for me, you don't need to do that, but some people would like you to do that. Any questions on that there? We typically can't go one place to the right, as I said, of the smallest marking, but not always the case. So for example, we had sort of the same breakdown there, 10 and 20 milliliters. Once again, in our graduated cylinder here, we'll go right about there. So our big markings, once again, here is 10 milliliters. The difference, though, is we now have 1 line, 2, 3, 4, and 5 markings, right? So each of the smallest markings in this particular case is how much? It has 2 milliliters. That would be 12, that would be 14, that would be 16, that would be 18. Now we see that our meniscus here is between 12 and 14, and between 12 and 14 is which number? 13, yeah. There's not enough room between those two to figure out where 12 stops and where 13 begins, right? So the best that we could do in this particular piece of equipment would be to call it 13 milliliters, which means this would have how many significant figures? Would have 2 significant figures. The uncertain number would be the 3 in this case, right? Telling us maybe it's 13, maybe it's 14, yeah, maybe it's 12, somewhere in that ballpark. The uncertain number is always the last significant figure. Let me say that one more time. The uncertain number, or estimated digit, is always the last significant figure, not necessarily the last number, but is the last significant figure that is in that particular number or value. We could still do our sort of precision here. We would take 2 milliliters divided by 2, which would give us plus or minus 1 milliliter, which is exactly what we took the reading to. Any questions on how to take proper measurements here? Yeah. So as I mentioned before, it is customary, and you should always record all the certain numbers plus that first uncertain number, which will give you your significant figures. Let's also talk a little bit about when we do take sort of measurements and some things that we look for, and that is accuracy versus precision. So those two names or two words actually do mean different things. Accuracy, or how accurate you are, tells us how close you are to the true value, the correct value, if you will. Precision, on the other hand, tells us how close, for example, a set of values are to themselves. So a lot of times when we do experiments, we do multiple trials, right? We repeat the same sort of process over and over again. The idea of that is to tell us about how reproducible our results are, right? How reproducible the experiment is. And that is about precision, right? Accuracy, and how accurate we are, is, how close we are to the true value. We sometimes look at something known as percent error to help us determine how close we were to the true value. Small percent error means we were pretty good. Large percent error means we were not so good. So if we threw some darts at a dartboard, the goal, right, is to get the bullseye there in the middle. So if I go, hey, let me throw my darts. Let me grab some darts. I throw it, I hit one here, I hit one here. Sadly, I'm not so good there. I missed its board completely. Hopefully nobody was standing there. Am I accurate? I'm not very accurate, right? That's all over the place. The true value would be, in this case, the bullseye, right? So I clearly did not hit the true value. Am I precise in this case? I'm not either. Those guys are really not grouped together, right? So I was all over the place. So I'm neither accurate nor precise here. I go, hey, we'll just do like a double or nothing, friendly wager, don't gamble, all that good stuff. So I take my darts and I throw them again, and I go boom, boom, boom. Am I accurate? No. Am I precise? Yes, I'm precisely not accurate, right? Which means it happens in life, right? If you kind of do the wrong thing every time the same way, you get the same answer. It's the wrong answer, but you do it wrong every time. So you definitely can be very precise, but not very accurate, which is definitely not what you're going for usually. You want to be a little bit of both. So I go triple or nothing here. I collect my darts, maybe. I collect my darts, maybe. They let me collect my darts. There we go. All right, so I collect my darts, a little bit of my ego, and I go triple or nothing, and I throw it. Am I accurate? Am I precise? And that's really what you want to go for, right? When you're doing experiments, you want to be accurate. You want to go for the sort of true value, what you're looking for. But you also want to be able to be very reproducible in your experimental procedures, right? You want to be able to reproduce the same results sort of every time. Any questions on the difference between those two? Okay. It's a much prettier picture than what I drew, but I think mine has a more, non textbook look. All right, let's take a look at this here. Hope nothing moved on the lines. I hope sometimes the lines move from PowerPoint, but I think we're good. So if we look at this here, we would want to look at the scale and figure out what we're looking at. So we have big numbers here and here. So the difference there is our 1 centimeter. We have 10 markings right between those two. So much like our previous example, that means each of the small markings is 0.1 of a centimeter. And that would mean that right about there would be 2.5. And that means we're at least 2.6, right? And if we think about our precision that we could do here, we could take it at plus or minus 0.5 centimeters, which basically means we should take this reading to 2 decimal places, right? That means I'm thinking we're going to shoot with a 2.69, and I just did my precision. So it should be something like 2.69 centimeters. And again, our precision there would be plus or minus 0.05 there. Here's another one. It's kind of the same idea. This is 8. This is 9. So once again, our big markings being 1 centimeter. Our little marking is going to be 0.1 centimeter. So it's at least 9. So we're looking for something for 9. Once again, if we calculated our precision, we would see that we can go to the second decimal place, which clearly eliminates that one, and eliminates that one, right? So it would definitely have to be here, which is 9.02 centimeters. Any questions on that there? Here's our graduated cylinder. And again, same idea as we sort of looked at here. In this case, we have 10, we have 40. So our big markings is going to be 10 milliliters. There are 10 lines between them, which means, again, each of our small markings, once again, will be 1 milliliter, which means if we do our little precision, you could take the reading to the first decimal place, right? And that means that if we come right about to this guy, that's 35. So that's going to be 36 right about there. And we're just above it. So 36.8, they estimated it to be. That would have how many significant figures? 3 significant figures. Estimated digit would be, the estimated digit would be the 8. Yeah, that's the estimated or uncertain digit. That's where the uncertainty basically lies in that measurement. Yeah. Any questions on that one? Now, sometimes, super zoom of the eye. All right. Now, sometimes we do use some other types of equipment, might be a little bit different than you used to. This is what's known as a Buret. You use it a lot for titrations. We'll use it right around experiment 11, maybe, or 10. I don't know. It's somewhere or down the road. Actually 20, I think, for you guys, or 21. It actually increases as you go down. So we fill the Buret from the top. You fill from the top, it drips out the bottom. And if you go to the very top of the Buret, it is 0. Then it is 1, then it is 2 milliliters, and so forth. So as you drain it from the bottom, the volume starts to drop. So when we are in this region, it's actually 1 point something, not 2 point something. So it reads a little bit different than what we were looking at before because of the way it sort of exits the volume out the bottom. So if we were to look at this, that's why we see 28 here. We see 29 here. Again, the biggest markings would be 1 milliliter. There's, again, 10 little markings in between, which means each of the smallest markings are going to be 0.1 centimeters, or milliliters. And that means that our precision, if we were to look at it, we could take it to 0.05 milliliters, which means we can read this to 2 decimal places. So this would be 29 right there. And this would be 28. And this would be then 28, 0.1, 0.2, 0.3, 0.4, 0.5. 0.6, 0.7, 0.8, right about there, and just a little below that dash, so 28.85 milliliters. Number of significant figures in this number would be 4 significant figures. The uncertain number would be in this case, it would be the 5. Yeah, in this particular. Any questions on that one there? So it's really important to make sure you look at the actual scale and figure out what the scale is. It does change depending on, you know, what piece of equipment you're looking at. That's another one. Let's actually talk about one other thing that's a very common mistake that people make. We'll go back to the ruler example. Ruler-ish. All right, so let's say we wanted to measure this guy right here. So take a moment and record what you think the proper reading should be. And I'm going to say it's right on that dash. So, okay, so let's take a look. So once again, we have our same sort of setup as we saw previously. Our big sort of values there is going to be 1 centimeter. We do have our 10 dashes between the two, which means each of our smallest markings is going to be 1 centimeter. So this would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, and so forth. Should the answer be 1.5 centimeters? Should it be 1.50 centimeters? Should it be 1.50000? Because more zeros feel more scientific when you're doing it. I'm going to say that just feels like a lot of zeros, that last one. So which one should it be? Should it be 1.5 or 1.50? Or is there a difference depending on which one you record? Does it really matter? 1.50, 1.5. Okay, so let's take a look at both of them and see really, you know, is there a major difference? We'll start with the 1.5. First off, how many significant figures would this number have then? It would have 2 significant figures, which means this number's uncertain value or digit would be the 5. So basically what you're saying here is, I think it's 1.5 centimeters, but maybe it's like 1.6 or 1.4. And clearly looking at it, it is like nowhere near either of those numbers, right? So that's a pretty bad measurement. If we look at 1.50, how many significant figures does this number have? It does have 3 significant figures. That 0 is significant because it was recorded there and there's a decimal point. The uncertain number would actually be the 0. And that means what you're saying here is, I think it's 1.50 centimeters, but maybe it's like 1.51, maybe it's 1.49. And that is pretty much what you are actually looking at on that piece of equipment. So it is a very common mistake that people make when they take measurements. They go, cool, it's like right on the line. Or probably more so, I'm not really sure how to properly take the measurement, but I see a big number written there, so I'm just going to write the number that's there. And they lop off, for example, a significant figure. And it makes a really big difference because, frankly, by doing 1.5, you made a pretty crappy measurement, right? There's a lot of error associated with that. We really sort of cut down on a lot of the error here. And we were able to do that based on the piece of equipment that we have. So you should never like lose really a significant figure when you're taking a measurement, because it really makes your measurement a lot worse than it actually should be. Any questions on that there? Any questions on how to properly take a measurement? By the way, if you have something that is digital, which is also another very common mistake that people make, if it is digital, all the numbers are important. So you should record all the numbers that you see, like on your balance today. You should record all the numbers that you see on the electronic balance, because they're all important. Any questions on measurements? Okay. Then let's talk a little bit about significant figures and the rules for counting significant figures. First off, the first rule for counting significant figures is pretty much anything that is a non-zero is going to be significant. We always start counting left to right on a number, and we start counting significant figures as soon as we hit the first non-zero. So in 1, 2, 5, 9, the 1 would be where we would start counting. So that would be significant. The 2, the 5, and the 9 would then be significant as well, which means we have 4 significant figures in that guy, in that particular measurement or number. It is the zeros that sometimes give people a hard time, and there's 3 different types of zeros. The first type of zero is the leading zero. So those are all the zeros that come before you hit the first non-zero. So we follow the same rule, left to right, and we do not start counting until we get to that number right there, as that is the first non-zero. Everything else is kind of like a placeholder. And we would start with the 4, which is significant, and the 9 is significant. And that would have 2 significant figures. The uncertain number would be the 9 in this case. Uncertain number above would actually also be the 9 as well. There's also captive zeros, or they're sometimes called trapped zeros. And those are zeros that come between 2 non-zero numbers. And those will always be significant. So once again, going left to right, starting at the 5, that is a non-zero, and that's where we should start counting. The 5 is significant. The 2 zeros in the middle are trapped, which means they're significant. And the 4 at the end is a non-zero, so it's significant. So it has 4 significant figures, with the 4 there at the end being the uncertain number, or the estimated digit. Any questions on that there? The zero that gives people the hardest time is what is sometimes referred to as the trailing zero. These are zeros that come at the end of the number, and they may or may not be significant. What makes them significant is there a decimal point anywhere in the number? Does not need to be near the zeros, but anywhere in the number, is there a decimal point? So if we wrote 600 like this, the 6 would be where we would start counting. It would be significant. The 2 zeros at the end would not be significant because there is no decimal point written. So this would have just 1 significant figure. If we wrote 600 with a decimal point there at the end, it would now have 3 significant figures, with starting counting here. And now these 2 zeros at the end are significant because of the decimal point that is there. So 600 like this, not significant. 600 like this, significant. This guy would have how many significant figures? The last one that I wrote there, this one would be? It would be 5. The 6 is significant, and all 4 of those zeros would be significant because there's a decimal point. This guy here has how many, if it was a measurement? We would not start counting until we hit here, and then that would be significant. These 2 would be significant. The 1 would be significant. Are the zeros at the end significant? They are, because way over here, there's a decimal point. So this would have 1, 2, 3, 4, 5, 6 significant figures. Finish up on where is the estimated digit in the 600 written like this? Which one is the estimated digit? The estimated digit, this guy right here has how many significant figures? 1, which means it is actually the 6. And that's what I said earlier when I said that the estimated digit is the last significant figure. A lot of times it is the last digit written, but not always. And this would be a case where it wouldn't be. That is a pretty crappy measurement. That is telling us that it could be 600, could be like 700, could be like 500. That's a pretty big range of, I'm not really sure, right? So it's not as good as this one, right? Right below it, where the uncertain digit would be which zero? It would be this 0, yeah, which tells us maybe it's like 601 or maybe it's like 599. So that's a much better measurement than the one above it. Any questions on any of that stuff there? All right, that was fun-ish.